Hello and welcome to our third section on group theory. At this point, we want to go to the details about how to extract more information about the group structure based on the information about the subgroup, about its subgroups. In order to motivate this discussion, let's take a concrete example. Let's say that we are thinking about the group Z, the integer modulo 6, and the member of these groups is 0, 1, 2, 3, 4, and 5. Now, also note that based on the proposition that we had stated in our first lecture, that Z6 is a cyclic group, so it will have a subgroup of order 2 and order 3, right? Now, consider the subgroup of order 2. Let's say H is its subgroup of order 2, subgroup of Z6, and you can see that H contains two elements because it has order 2, 0 and 3, and they form a subgroup under same addition. Now, if I want to view this entire thing pictorially, let's say that this is my Z6. And note that with respect to the generator of this subgroup, which is 3, modulo the generator of this subgroup, which is modulo 3, this entire group Z6 can be partitioned into 3 partitions, right? So the first one is H itself, okay, which is, and it contains 0, 3. The second partition is, let's denote it as H plus 1, which means it will contain 1 and 4. And the third partition has H plus 2, and the elements are 2, 5. Okay, now this makes sense. This is the reminiscent of your residue class, right, that you have seen in your undergraduate course. And it's a residue class modulo 3, modulo the generator of the subgroup. And also note that it has some nice properties. So H is the subgroup of Z6. That means H itself is a group. H plus 1 and H plus 2, they are not groups. They don't form a group because they don't have the additive identity, which is 0. They are rather sets, subsets of Z6, but the size of all these 3 sets, if we view it that way, H, H plus 1 and H plus 2, they are same. They all contain 2 elements, right? So if we think residue class in this way, that's exactly how they partition the original group. Good. Now what we're going to do, we will extend this idea in a little bit abstract form, right? So far this entire example revolves around a cyclic group that we have taken, but it doesn't have to be. So let's extend this entire idea in general for a group and see what group structure we can unravel through this argument. And at the end of this section, we will see that there are some very powerful tools that comes out, and we call this the Lagrange Theorem, and we will prove that. Okay, let's move on. Okay, now in order to extend the concept of residue class for an arbitrary group, we need to introduce some definitions corresponding to some new mathematical object called coset. So just like a number can have residue classes, a subgroup can have cosets. So let's start with that. Coset of a subgroup. Okay, now here is our general setting that H is a subgroup of G, and we are not imposing any restriction on the group G. It can be abelian or non-abelian. So not necessarily the group multiplication commutes. So we have to consider the left coset and the right coset separately. So let's start with left coset. So left coset of H generated by an element G belongs to G. So remember that this entire thing is needs to be specified, because left coset of H doesn't make much sense unless I say that generated by which element. And as it will be clear when I give you the definition. So the definition of this thing, so this is going to be a set which is denoted as the element G times the group H, and it is defined as what it means, GH, such that H belongs to H. So essentially, left coset generated by an element G is the set that you obtain by multiplying each member of the subgroup H with that element G. That's what it means. Similarly, we can consider the right coset of H generated by G, generated by G, and as you can imagine, it goes like this: Hg such that H belongs to H. Okay, with the definitions of cosets, let's adopt a convention that unless otherwise specified, we will only consider the left cosets. Okay, good. So the first question is, when is the coset generated by an element A and the coset generated by an element B, when are they going to be equal? Now take it as your homework exercise to convince yourself that this is true. Actually, it is true if and only if it implies both ways, that it happens when A inverse B belongs to the subgroup H. Okay, now if it is true, then we can actually define an equivalence between any two element in the group. So for example, we can say that A is equivalent to B, where A and B belong to the group G, when A and B belong to the same coset. Or in other words, A inverse B belongs to the subgroup H. Good. Now, as you know that every equivalence relationship has an equivalence class, now we can consider equivalence class for this equivalence relationship here as well. Equivalence class of any element, let's say equivalence class of A. Okay. Okay, and the way it is defined as essentially this equivalence class is the coset generated by A, or in other words, containing elements X such that X inverse A belongs to the subgroup H. And as it follows directly from the definition, that this is same as the coset of A. Okay, good. So, and what you can see probably here, that these are the equivalence classes that correspond to the residue classes that we have seen in our earlier example. Great. Now we will establish a very important relationship between the number of such equivalence classes, or the number of cosets, and the size of the subgroup and the size of the original group, known as Lagrange Theorem. And it gives us a very important and powerful tool in understanding the group structure. Okay, so one final definition before we go to Lagrange theorem. So notice that we can consider a map between a coset AH, which is a left coset, to a right coset HA inverse, let's say. Now, this is actually a one-to-one correspondence, which essentially implies that there are as many left cosets. So, number of left cosets of any element A is same as the number of right cosets. Now, therefore, and we also know that the number of cosets for any finite group, it has to be finite because they are the original group is finite. So now we define something called index of H in G, where H is a subgroup of G. And the way it is denoted as index of H in G, and the definition is the number of cosets of H generated by all the elements in G. Okay. Okay. With the index defined, here is what Lagrange theorem states. So Lagrange theorem says that if H is a subgroup of G, then it will imply that order of G divided by order of H is the index of H in G. It's that simple. Okay, so let's prove it. Okay, so before giving a formal proof of Lagrange theorem, let's take a look at what we have. Okay, so what we have is a group G, and then we have a subgroup H, and we also have some cosets that we can denote as AH, BH, and so on. Now, it seems that we can prove Lagrange theorem if we can show two things. Number one is cosets are non-overlapping. That means if you take any two arbitrary coset and their intersection will be a null set. And number two is that size of any coset, let's say AH, is same as the size of the subgroup H. That means if we can show that all the cosets are of same size, and that size is the size of the subgroup H, and they are non-overlapping, then we can prove Lagrange theorem. Why? Because any member in the group must belong to any of the cosets. And the coset in that case will partition the entire group exactly the way Lagrange theorem says. Okay? Okay, good. Let's work one after another. So, number one. Now, let's say that X is a member that belongs to the coset generated by A. And we will prove by contradiction. Therefore, let's also assume that X also belongs to another coset BH such that A and B are not equivalent. Otherwise, they will have the same coset, right? But X belongs to AH will imply that X is equivalent to A. Similarly, X belongs to BH will imply that X is equivalent to B. These two combined together will imply that A is equivalent to B, but that's the contradiction because we say that A and B cannot be equivalent because otherwise they are the same coset. Okay, great. So that proves number one. Now for number two, let's consider the subgroup H and any arbitrary coset AH. And notice that any arbitrary member of this subgroup H, we can think about a map so that H gets mapped to AH. Now, notice that this map is bijective. Why? Because for any element AH in this coset, there is an inverse. You can left multiply with A inverse and you can get back the H, the element of the subgroup itself. So for every element, there exists an inverse of this map, which means that this map is bijective. Okay, so since this map is bijective, it will imply, therefore, that the size of H is same as the size of the coset AH. But we actually assumed AH to be any arbitrary coset. So number 2 is actually proven for any arbitrary coset of the subgroup H. Okay, so this part is done, and combined together, this actually proves our Lagrange theorem. Okay, good. Now, with the Lagrange theorem proven, we have a more interesting question to ask, which is what about the converse of Lagrange? What about the converse of Lagrange theorem? Well, Lagrange theorem essentially says that if H is a subgroup of G, then Lagrange theorem implies that the order of H divides the order of G. It doesn't say anything about the converse. But we can actually show, just generating a counter example, that converse is not in general true. So for example, remember the alternating group? Consider the group A4. Now we know that the order of this group is actually 24 divided by 2, which is 12. Now we also know that 6 divides 12, but you won't be able to find any subgroup. So no subgroup of order 6 exists for A4. Now, take it as your homework exercise and use those cycle notation and show that. But this is what you will find. You won't be able to see any subgroup of order 6, which essentially says that this is the counterexample, and in general, the converse of Lagrange theorem is not true. Okay, but it would be excellent if the converse would be true. Then we could actually construct the subgroups just by looking at the order. Now, even though the converse is not true, there is something that we can do. First of all, we have seen in our first lecture that the converse of Lagrange theorem holds true for cyclic groups. For cyclic groups. In fact, this is I will prove without any. I will state this statement now without any proof that the converse holds true for any abelian groups as well. And we don't have the necessary tools right now to prove this statement, but we will come back to it later. Throughout this course, we will always have in the back of our mind that how much of the converse of Lagrange theorem that we can recover, right? Of course, we have seen that it is not going to be true for all the groups, but eventually we will see that for a broader class of groups, the converse of the Lagrange theorem will hold true, and we need to know what that big family of group is. Again, without any proof, or I haven't even defined that, we will show it to a broader family called nilpotent groups, and that will automatically imply that this is true for abelian groups. So we'll get there. But now some examples that we can generate from Lagrange theorem. Okay, let's now discuss the application of Lagrange Lagrange theorem. So the first one, let's draw from your undergraduate knowledge in number theory or group theory maybe. So just to remind you that any number a is called a unit mod n if a has a multiplicative inverse mod n. That means there exists a b such that a times b is congruent to 1 mod n. Okay, so this is something that you have seen. Now also know that units mod n, for example, form a group. And it is denoted as u subscript n, right? Now, you can see that probably, unless you don't remember, said, of course, if A and B, they are unit, everything is abelian here. So then A times B also has a multiplicative inverse because I can always do A times B times A inverse B inverse. So therefore it is closed. Regular multiplication obeys associativity. Identity is 1, and because 1 already has an inverse, and units are defined to have an inverse, so inverse criteria is not a problem. So it satisfies all the group criteria, and therefore un is a group. Okay, now also let me quickly remind you another thing, that any two number, let's say um, a and n, the GCD of a and n equal to 1, if a and n are relatively prime, then you can always say that it implies both sides, that you will always find a b such that ab is congruent to 1 mod n. And this implies both ways. That means in order to belong to the group of units, um, that number has to be relatively prime modulo n, right? And why it is true? This is coming from essentially Bejour's lemma. So because GCD an equal to 1 will imply that you will find numbers x and y such that ax plus ny equal to 1. And in the notation of mod n, it, as you can understand, that it means ax is congruent to 1 mod n because ny is divisible by n. Okay, good. So um, we have done a recap on what is the group of units and why it is a group and what it takes to belong to the group of units. So any group of units modulo n, in order to belong to that group, that number has to be relatively prime with n. Okay, now having said that, let's ask a question, that what is the order? So what is the order of un? Well, I mean, that's also a little bit, I would say, obvious from the definition, because in order to belong to this group un, um, any number, and by the way, this number we are talking about modulo n, so the options are, of course, 0 to n minus 1, and not all of them can belong to this group. And in order to belong to this group, that number has to be relatively prime with n. So the order of un is going to be the Euler-Totient function phi of n, which is the number of integers that is co-prime with n. Okay, Um, Great. Now, what it means essentially, if we apply um, Lagrange theorem, that what it will mean that if A belongs to un, then it will imply that the order of A, right? Because I can think of a group generated by A, which is going to be a cyclic group under un, and it's going to be a subgroup of un as well. And therefore, the order of the cyclic group must divide the order of un, which is phi of n. So that means what I'm going to get, that e to the phi n must be um, 1 mod n. Now remember that so i- actually whatever the order of A is, that must divide phi n, which automatically implies this relationship, right? Now this is actually our famous Euler's theorem. So it's a little funny that Euler probably first proved it in around 1736, and then he couldn't prove the general result. So there's, of course, a corollary of it. For example, when n is a prime, then you know that if if n equals to p prime, then it will imply that phi of n, which means phi, what I mean is phi of p, is actually p minus 1. And that will imply that a to the p minus 1 is congruent to 1 mod n, mod n. Okay. But this result is the corollary, which is often known as Fermat Little theorem. Little theorem, right? Now, Euler first proved this Fermat-Little theorem version of Euler's theorem in 1736 and maybe generalized it later in 1763. The proof was probably a few pages long and using the number theoretic argument, etc. But it's interesting to see that how abstraction helps um, proving a mathematical statement way more efficiently. So this is kind of a one-line proof using the group theoretic technique, that we are kind of getting Euler's theorem for free, essentially, based on the structure of the group. So the group of units that itself is not a cyclic group, it's an abelian group. Now I can take any member from that group and I can construct a cyclic subgroup, and then I can use the Lagrange theorem and say that the order of that cyclic subgroup must divide the order of the group of units, and that gives me this Euler's theorem. Okay, so this is our first example. Okay, let's look at another very simple but very powerful corollary that is coming from Lagrange theorem. So the proposition is the following, that if the order of a group G is prime, then this will imply that G is cyclic. Okay, the proof is maybe just one line. I can consider any arbitrary element A that belongs to G such that A is not equal to identity. And now I can ask the question that what is the order of this A? So I know that the order of this A must divide the order of G. And if that is true, then what are the options for the order of A? Because the order of G is prime and our order of A is not 1. So the only option is that the order of A is same as order of G, because order of G is not divisible by any other number other than 1 and the order of G, right? Now, since the order of A is same as the order of G, now I can take a look at the group generated by A. Now, this group has the same number of element as the original group G itself, and A is included in G. So that will imply that the group generated by A is same as the group G. And therefore, G is generated by a single element. So that will prove our assertion that G is cyclic. So the proof completes here, but it actually tells you something more than that. It also says that any arbitrary x belongs to G um, for all x. Um, x is a generator. X is a generator of G. So not only it's cyclic, any element is the generator of the group itself. Okay, now this is very powerful in the sense that if you look at the order of a group, and if you identify that that's a prime number, you can immediately understand the internal structure of the group, which is cyclic, which is that it's cyclic and it's generated by any element of the group, right? Okay, now let's prove a corollary that is coming from Lagrange theorem, but it's slightly more involved. So what it says is that if I have a group K, which is a subgroup of H, and H is subgroup of a G, then that implies that index of K in G is same as index of H in G times index of K in H. Okay, so the group indices are multiplicative for nested subgroups. That's what it means. Okay, now first of all, why is it involved and why is it interesting to begin with? Isn't it true that I can write the index of K in G using Lagrange theorem as the order of G divided by the order of K, and then I can write this as order of G divided by order of H times order of H divided by order of K, and then finally I can rewrite it in the index notation, which looks like what we wanted. So the index of H in G times index of K in H. So doesn't that prove this theorem? Well, it does, but the point is that this can prove this theorem when the group G is finite. Okay. Otherwise, dividing by the order of a subgroup doesn't make any sense. But the main point of this proposition is that multiplicativity of these indices will hold true even if your groups are infinite. Okay, and one quick example, of course, is we know that Z, the group of all integers, that's an infinite group, and group of multiples of 3, for example, that's also an infinite group, but this is a subgroup of Z. But 3Z has 3 cosets in Z, which are the residue classes modulo 3, right? So we have this situation, and we need to make sure that this proposition, this multiplicativity, holds true even when the groups are not finite. So let's work on that. But first, let's do something. Let's try to prove. Before even we go for the proof, let's see what we have, and let's create a pictorial representation of the statement itself. So what we have is the following: we have a big group G, and then we have a subgroup which is H, and inside that subgroup H we have another subgroup that is K, right? So the setting is the following, as we said, that K is a subgroup of H, which is a subgroup of G. Okay, now what we can do is, in order to visualize, we can think about the cosets of H and G, and let's write them down. So let's write the cosets of H as A1H, A2H, all the way to A sub M H. So these are the cosets of H in G, and therefore it will imply that M is same as the index of H in G. Okay. Okay, good. Now let's write down the cosets of K in H using a different symbol. So B1K, B2K, all the way to B sub N K. So these are the cosets of K in H. Remember, not the cosets of K in G, the cosets of K in H. And therefore, this will imply that the number of such cosets is same as the index of K in H. Okay? Okay, now a very important observation, and try to follow this logic. So if I think of any arbitrary coset of K in G, so let's say that CK is a coset of K in G, then I know that then we can ask a question first, that where does C belong to? So C must be in some coset of H in G, right? C must belong to the group G, and therefore C must belong to one of these cosets, because these cosets partition the entire group. Now, without any loss of generality, let's assume that C belongs to a coset called AIH. C belongs to here. Now, if that is true, then it implies that C must be written as AI times some H, where H belongs to the subgroup H. Okay. Now, the second part of the logic, if H belongs to the subgroup, if small h belongs to the subgroup H, then the small h must belong to some coset from this set, right? It must belong to some cosets of K in H using the similar logic. And then assume that H belongs to the coset BJK. Now, if that is true, then everything what I'm saying here will imply that C must belong to AI BJK, right? So, which essentially means that the coset generated by C is same as the coset AI BJK. Okay, good. So, after this point, what we can say is, notice that this CK is, I have chosen this for any arbitrary coset of K in G, and therefore this map from any arbitrary coset CK to the CK that gets mapped to some ordered pair AI comma BJ. right? Now, notice that this map is um, bijective, because the way I'm constructing it, it's onto it's surjective, and for every coset ck, these I and j, they are unique. The uniqueness is guaranteed by the property of cosets themselves. Any element can only belong to only one coset, right? So therefore, this is injective as well. So injectivity and surjectivity tells you that this is a bijective map. And this bijectivity will essentially imply that the total number of cosets must be total number of cosets of k in G, which is index of k in G. It must be same as the number of ways I can choose AI and BJ. Now I can choose AI in m number of ways, as you can see here, and of course I can choose BJ in n number of ways. So it must be same as m times n, and which is equal to the way we have defined them, which is the index of h in G times index of k in H. Okay. Now, this actually formally proves the theorem, but if you want to reflect a little bit and try to take a look that how does it look in this picture, all it means that the cosets of this subgroup K, it has all its copies, not only in the subgroup H itself, but also in all the cosets of H. Okay, so in all the cosets of H. So essentially, if you think about it geometrically or in a pictorial sense, it's counting all the cosets of K in G. It means counting the number of cosets of K in all the cosets of H in G. So essentially, it's counting the smaller rectangles in the bigger rectangle of G, right? So that's where the multiplication is coming from. Okay, good. So this is telling us that this multiplicativity of the indices will hold true no matter if the group is finite or infinite. And we will make use of it later. Great. So these actually concludes our discussion on the cosets, Lagrange theorem, how to understand the structure of a subgroup using Lagrange theorem. And in the next section, we will start another important discussion called normal subgroups. Thank you.